Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is the presentation for section 1.4, continuity and one-sided limits. So let's get right into it today. We're going to try and understand the definition of and how to apply continuity. And then we are going to determine a one-sided limit and continuity on a closed interval. And then finally, we're going to apply the intermediate value theorem. Okay, so first, the definition of continuity is on page 70, and basically it entitles 3 parts. And definition continuity at a point, and continuity is usually defined at a point. So is it continuous at this point right here? Is it continuous at this point right here? Is it continuous at this point right here? And then make a statement about the interval on which the whole function is continuous. So if I want to say it's continuous at any given point, and then if it's given on all of the points, then it would be over some interval. But if it's continuous at, say, some point C here, so let's pick a point here and say, okay, there's my C. F of C has to be defined, and clearly we can see that F of C is certainly defined. It's this point right there. There's F of C, whatever that value is. And then the limit of f of x exists as x goes to c. And then, so if we follow our rule for limits, as I approach it from both the left and the right, it looks like it points to the same value. So that is true. And finally, the limit and the function are both equal. All right, so or the function at c. So the limit and the value of the function at that point c are both equal, and clearly we can see that to be true. Now, as a for instance, if I were to say, let's say I erase this point right here and have a circle right there, and then a point up here, well, f of c is defined. It's this point here. This f of c has to move up. The limit exists. It points to the same thing, but this third one does not hold true. All right, the limit and the value of the function are not equal. So in this case, it would not be continuous at C. All right, so let's move that all back and put that all back so we can see it. All right, let's talk about discontinuities. I've shown you one discontinuity, and we talk about removable versus non-removable discontinuities. And so I have this function here, and this function has a hole at A. There is a vertical asymptote at B, and then at this C, it jumps from up here to down there and then continues on in a horizontal line. So graphically, a removable discontinuity is a discontinuity where the limit still exists, but the value of the function doesn't exist, or the value of the function is not equal to the limit. So that would be a removable discontinuity. A non-removable discontinuity is where you have more than one of these things not happening. Like the value of c is not defined, the limit doesn't exist. And so here, since this one has a limit that goes up, this one has a limit that goes down, the value of the function doesn't exist, and obviously the value of the function, if the value of the function doesn't exist, the limit doesn't exist, well, the limit wouldn't equal the function, so there's all three are missing. This one, the limit doesn't exist, the value of the function does exist, but since the limit doesn't exist, the value of the function and the limit can't exist, so it's also non-removable. So we can see that there's one removable and one non-removable. So one of the type of questions that you're going to get asked is they're going to give you a function and they're going to say, discuss the continuity of the following function over its domain. And so I look at this function. This is a rational function. Usually you won't get it factored like this. You'll probably have to do some work on your own before you get to do your discussion. And that will be to say, okay, I've got this function here, and I have two values where the function is undefined. So here we can say that f is undefined at both x equals -2 and x equals +1. Now you'll notice that this x minus 1 and this x minus 1 would technically cancel out. But when I do that, I get a new function, okay? So we can talk about this function over its entire domain. So I have discontinuities at f of x equals -2 and x equals +1. So here's what I want you to do. I want you to take a minute and pause this video and graph this function on your own. Just kind of graph it and take a look and see what you come up with. All right, so I'm going to pause here, give you a second to take a look at it. Pausing for 1, 2, 3. Now, when you looked at that video, hopefully you saw that there was a vertical asymptote at this x equals -2. And that vertical asymptote, as we showed in this previous slide, is a non-removable discontinuity. The thing that you should have seen, especially on the graphing calculator, is we already know that at x equals -1, the function is undefined. And if you set up a table in your graphing calculator, it probably would give you a error for the function value at x equals 1. All right, but if you look at the graph, it probably looks continuous at 1. And this is me just guessing here real quick, but it probably does something. Let's see here. -3 probably does something like this, I'm guessing. And if you're looking in your graphing calculator at 1, it doesn't look like there's anything missing, but we do see that there is an undefined there. So one of the shortcomings of the graphing calculator is the fact that it does not show these removable discontinuities. All right. So what we can do here is we can say that this function is continuous on its domain, and that domain being all values of x except for -2 and +1. And then we can say with a removable discontinuity, ti, I don't know why I put an e there, I, discontinuity, N-U-I-T-Y at, the removable one is the one that cancels out, so at x equals 1, and a non-removable discontinuity at x equals -2. All right. Okay, moving on. All right, talk about continuity on a closed interval, and let's review some interval notation. So I'm just going to draw a couple quick graphs here, and then we're going to talk about some intervals and the notation here just real quickly. So I'm going to, oops, I don't want that. This is kind of review stuff, because people always tend to, there's a lot of interval notation in calculus, and a lot of people tend to forget. So A, B. So interval notation. Let's say I have a function here, and I want to go to here. All right. So the interval for A to B in this particular case is A to B. So brackets include endpoints. And so if I got rid of these two dots here at the end and I put circles there, we would change it and call this A to B like that. Parentheses, exclude endpoints. All right, and so it also stands to reason that we could have an included one endpoint and exclude a third, exclude another endpoint. So let's say I had something like this, where it was closed in on one side and open on the other side. Well, this would be A with B open. All right, and just as a remember, And if you use infinity as an endpoint, all right, so whenever you use infinity as an endpoint, so if I go like from infinity to b, I can't include infinity because there's no such thing as an end to infinity. It always goes on forever, so it's never ending. So we can't include something, but we could include b, so that's also acceptable. All right, and let's see here. Oh, before I get into it, yeah, continuity in a closed interval, and again, if you read this in the book, it defines it more specifically, but you can talk about continuity on this interval. So this thing can be continuous at A because it exists. Now we say it only doesn't have a left-sided limit, but it does have a right-sided limit. So if it has an endpoint, to be continuous at that point, it just has to exist, and the limit from whatever side you're coming from has to equal that value at A. So you don't have to have the entire limit. Whereas it is discontinuous or not continuous at B. The limit exists. The right-sided the left-sided limit, that's a right-sided limit. Left-sided limit exists, but it's not continuous. So formally defining what left and right-sided limits are. And so a right-sided limit is going to have, and I don't know if you can see it here, but so I'm going to highlight it. A little plus, so a right-sided limit, that means you're coming in from the right-hand side. The left-sided limit has a little minus right there, so you're coming in from the left-hand side. And so when we talk about a picture here, let's get the right pen. So if we're coming in at C, the left-sided limit is just the value there. The right-sided limit is just the value there. We could also talk about functions that have different left and right-sided limits. All right. Let's draw it like this. Draw to C here. And let's call this point A. Let's call this point B. Let's call this f of x. All right. And so let's erase this. Okay. Let's clone this. And we're talking as just as an example. Clone. Let's move this over here. So this right-sided limit here. So I'm coming in from the right-handed side. I'm trying to see what happens as I come in from the right. Well, that limit is B. And then as I come in from the left side, let's clone that, move that over here. Coming in here, that limit is A. All right. So both of the left-sided limit and the right-sided limit exist. But if I say what is the limit as x goes to C of f of x, because these two are different, this does not exist. So the limit does not exist. It goes to two different values. All right, let's talk a couple properties of continuity. I would take a check at page 79 and read through some of those other properties, but just some high-level, real quick stuff before we move on to the next thing. Functions are usually continuous on their domain. That's not 100% true, but usually that is true. Especially, it's not true, especially when you come to things like piecewise functions. Polynomials are continuous on the real numbers, so a polynomial number is pretty much continuous wherever. A rational function is continuous. Again, it's continuous on its domain, but where doesn't the domain exist? Where the function is not equal to 0. So anywhere where you have a division by 0 is going to be a discontinuity. Radical functions are continuous everywhere, provided that the radical does not produce an imaginary number. So you can't take the square root or the fourth root of a negative number, and that would be a discontinuity. And trig functions are continuous on their domains. If you remember, only two of the functions, sine and cosine, are going to have be continuous across the entire real number line. Tangent, cotangent, secant, and cosecant, those all have asymptotes in them, and those are values where the function is undefined. So even though it's continuous on their domain, the places where it's undefined, where you get those vertical asymptotes, those are going to be removable discontinuities. Okay, intermediate value theorem is a fairly straightforward one. And so basically it says this: if you have a function that is continuous from A to B, so over some interval A to B, and there's no breaks, there's no discontinuities there. It doesn't matter how I draw this curve, every value has to exist between F and B. So any value K that I pick, there has to be some value C in between A and B such that F of C is equal to K. And that's all that means. So if you have a continuous function from A to B, then any value from F of A to F of B must exist in between there. You can have nothing that miss as long as that function is continuous. All right, let's hit some examples here real quick. Let's find the limits if they exist. Talking about left-sided limits and right-sided limits. I've got mostly right-sided limits here. And so a lot of the rules that we had from finding limits analytically in the last section still apply here. If I say what is the limit of f of this function as x goes to 3 from the right side, well, 3 does not make this function undefined. So this function is defined, and it's a rational function. So I can just plug this in and say that this is 2 over 3 plus 3, which is 2 over 6, which I think is 1/3. Now, unfortunately, in this second one, when I say what is the limit as x goes to 4 from the right-hand side, unfortunately, what happens is when I plug in 4, 4 minus 4 is 0. 4 squared is 16 minus 16 is 0. I have an indeterminate form. I had 0 divided by 0. So let's see here. The limit as x goes to 4 from the right-hand side, let's factor the bottom and remember a squared minus b squared is equal to a minus b times a plus b. So we can go x plus 4, x minus 4 over 4 minus, I did that wrong, 4 minus x. So that's not real good. So let's go limit as x goes to 4 from the right-hand side. I'm going to factor out a -1. I'm going to do it in 2 steps, and you're going to see this happen a lot to try and make something that I could cancel out. So I'm going to factor out a -1, and there'll be -4 plus x now over x plus 4 and then x minus 4. And if you remember, addition is commutative, so I can commute the -4 and the x, and I'll get the limit as x goes to 4 from the plus. That should be a plus, not a 4. Hopefully you can see that. Okay. And then I have negative. It'll be x minus 4 there over x plus 4, x minus 4. And so now I can, again, we're changing the function, but the limits are the same because I'm doing a replacement here. And then it'll be -1 over x plus 4. And then I can do something like I did in the first one, and then that would be -1 over 4 plus 4 is 8. That's going to be my limit there. Find this limit, and I picked this one because we're going to see stuff that a lot of delta x's, especially in the next chapter when we get into derivatives and using limit to define the derivative. And so I wanted to do one with some delta x. What happens as the limit as x goes to 0 from the right-hand side? And again, if I let x go to 0, I get an undefined in the denominator, so I just have to be careful. And basically what I'm going to try and do is I'm going to try and cancel something out just like I did here where we canceled these two. I have to do a little bit of work though. Remember, a plus b squared is a squared plus 2ab plus b squared. So I'm going to do that square first, and again, not taking the limit, and you saw it in this last one before. Until I actually take the limit, I write the limit every time. Don't lose a point because you write the limit here, and then just forget about it until you get to the end. All right, you got to write the limit until you actually evaluate the limit. All right, so back to this one. So I'm writing my limit as delta x goes to 0 from the right-hand side. All right, so doing this square, I get x squared plus 2x delta x plus delta x squared plus x plus delta x minus x squared minus x, and I'm distributing the negative sign to both terms. So I have delta x on the bottom. And again, I haven't evaluated the limit, so I'm writing it. Goes to 0 from the right-hand side. I need a plus. All right, and so I got a negative. I got x squared, negative x squared, that cancels. Positive x, negative x cancels. That leaves me with 2x delta x plus delta x squared plus delta x all over delta x. Now you can see all three of the terms in the numerator have a factor of delta x, and we have delta x on the bottom. So what I can do is I can say that this is the limit as delta x goes to 0 from the right-hand side of now just 2x plus delta x plus 1. And again, just a common mistake that I see, and don't make that mistake. I see a lot of kids who will go, well, delta x divided by delta x is 0, because they cancel, quote unquote. But remember, delta x over delta x, and that's what we're doing. We're doing a fraction. We're doing each of these individually. Delta x divided by delta x is 1. Don't make that mistake or you're going to miss a few points. Now, even though this thing, if it goes to 0, becomes 0, it doesn't become undefined anymore. So I can let all of these things go to 0 and say that this is just 2x plus 1, whatever that might be. And then there was no AP calculus lesson that wouldn't be complete without a piecewise function. So we want to determine the intervals on which this function is continuous. And so we're going to do a little bit of that interval notation. And so let's look at this function here. So I get x squared minus 4. That's a linear equation, and that's going to be true everywhere except for when x is not equal to 3. All right, so everywhere x is not equal to 3, then it's going to be this function, and then when x equals 3, it's going to be 1. Okay, so what does that look like? That's not too bad. We know that I need to make smaller, less thick lines for my presentations. I'll try and keep that in mind. Anyway, let's go. Sorry, got off topic. Here's my y-axis, here's my x-axis. Here's negative 4, that's the y-intercept here. And then if I let x equal 2, I'll get 0. So we'll put 2, 0 there, and then we'll connect the dots with another line right here. And then again, that should be, I don't want to do that. I want a solid. Let's do this, because I want to put a 3 right here. Now, if I plug 3 times 2 is 6, minus 4 would be 2. And so I have a graph that looks kind of like this, and then at 3 I have a hole because it's not equal to, and at that point it'll be equal to 1, right? And then from that point on it'll continue to be that line again. All right, so I have a removable discontinuity. Now the function exists at x equals 3, but it's still a removable discontinuity. So there is a discontinuity here, and if I were to change this to say 2, we would say that the function is continuous on the entire real numbers. But since there is a removable discontinuity, there is a discontinuity at the point 3, and it fails. If we go back just to kind of review, I know this is going long, but just to review, f of c is defined, the limit exists, but the limit and the function value are not the same in this particular problem. And so f, let's get a tool, f is continuous. Let's see here, it'll be continuous from negative infinity to 3. And then we're going to join that up as a union with from 3 to positive infinity. And so this basically says from negative infinity to positive infinity, excluding 3, and that is interval notation. All right, I know that's been a long time sitting there, 25 minutes, but we'll get to the end here. The Star Wars Super Fabu fun fact of the day goes back to Star Wars Episode 4, and we're in the trash compactor scene where Luke Skywalker is attacked by a underwater trash-eating monster. And during filming, and the fun fact of this is during filming, he had to hold his breath so long because they held him underwater because they wanted to get the water to be calm when he went underwater. He had to hold his breath so long that he actually burst a blood vessel in his eye and got like red blood in his I think it's called the sclera, the white part of your eye. And so they only filmed him from this angle because his other eye has all kinds of blood in it. So you only in Star Wars you only see what I guess would be his right side because his left eye is full of blood. Well, that's all I got today. I know that's kind of morbid to end with, but you guys have a good day, and I will see you in class. Goodbye.